Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light, where we've been looking at the work of Christian Huygens. Christian Huygens wrote his famous Treatise on Light in about 1690. We were exploring how Huygens was very interested in understanding not only the laws that govern how light travels, but the underlying principles that give rise to those laws. Specifically, he's going to argue that light behaves like a wave. In fact, he's one of the first advocates of the wave theory of light. You might recall that his opponent, Newton, believed that light travels like a particle from here to there, whereas Huygens is going to argue that light travels like a wave, analogous to sound waves, although different in important respects. We were studying specifically some of the early experiments on the speed of light. Descartes tried to measure the speed of light by observing the eclipses of Earth's moon. Since the moon is so close to the Earth, and since light travels so fast, he was unable to detect the speed of light, and so he thought that light traveled instantaneously, that is, at infinite speed. Olaf Romer, on the other hand, observed the eclipses of the moons of Jupiter, and in so doing he was able to determine that light travels at such a speed that it takes about 7 minutes to get from the sun to the Earth. 7 or 8 minutes, according to modern measurements. In any case, the speed of light is finite, very fast, but finite. And what Huygens is going to argue that light, due to its enormous speed, must spread like a sound wave and not like a projectile, as Newton thought. So you might think about other things that move like projectiles, like arrows or even cannonballs or bullets. They travel very, very quickly, but the speed of light is enormous even compared to the fastest projectiles that we can construct. Sound travels at about 330 meters per second through air, but it can travel much faster through solid materials such as water or through metals. And so the enormous speed of light, Huygens thought, gives rise to the idea that light is more like a sound wave than like a projectile. This brought us to about the bottom of page 164 in a Student's Guide to the Great Physics Texts. We're looking at the third full paragraph where he says that this, however, is quite another thing from being instantaneous. He's referring to the enormous speed of light, since there is all the difference between a finite thing and an infinite thing. So there he's criticizing Descartes' idea that light travels at an infinite speed. He says it's finite, but very fast. He says, now the successive movement of light being confirmed in this way, that is, it takes time to move from the sun to the earth, the successive movement of light being confirmed in this way, it follows, as I have said, that it spreads by spherical waves like the movement of sound. Okay? So here he's saying he's going to be using sound as a way of understanding light. So let's look at the fourth paragraph now. That's at the bottom of page 164. And there he argues that although light behaves like a sound wave in some respects, it differs in other important respects. And specifically, it differs in its mode of production, that is, how it is made. It's the matter in which it spreads, and finally, the manner or the way that it propagates through this matter. So he's going to, in the next page, he's going to explain these three important differences between light and sound. So let's first take a look at the production of sound. How does light differ from sound, assuming that it does travel like sound, or it's analogous to sound. And so it differs in three ways. The first way it differs in its production, how you produce it. And this is what he talks about at the bottom of page 164. He said that sound is produced by the agitation of an entire sonorous body. So you might think about when you have a bell, how does the bell emit sound? Well, what happens is the entire body, the entire bell, when you strike it, it vibrates. And as a result of vibration, that compresses the air around it and expands the air around it, and that causes sound to spread out from around the bell. So it's kind of a vibration of the entire sonorous body. So sound is created by vibrations of an entire, he would say, sonorous or sound-making body. Light, on the other hand, he says, arises from the agitation of the individual points within the body. By vibrations of the individual points, or you might say the atoms, within the body. And he uses as an example, a lump of charcoal. So if you have this charcoal right here, and it gets very hot, it's not like you're striking it with a hammer and seeing the entire thing vibrate. Rather, the entire thing is agitating on a molecular level, and as a result of that, there are light waves that come out from it. So there is a vibration, but it's on a more molecular or atomic level, according to Huygens. So that's one important distinction between the creation of light and the creation of sound, or the production, as he would say. Now, what's the next way that sound and light differ? He says they differ, and this is at the top of page 165, the first full paragraph. He says they differ in the matter, in the matter in which the wave spreads. Okay, now what's the distinction then between the matter in which sound spreads and the matter in which light spreads? He says that the sound waves, you might say, the sound waves spread in the air which we breathe. So that is the medium that is being compressed and expanded when sound waves travel. And on the other hand, he says the air we breathe is not the medium that's responsible for the propagation of light. He says light waves spread in an ethereal matter. It's a different kind of matter, a different substance, an ethereal matter, which is distinct from air. And he's going to be spending the next many pages trying to understand what are the properties of this ether, this ethereal matter in which light is spreading. Now, first of all, why would he believe this? Why would he believe that the medium in which light travels is different than the medium in which air travels? Well, he gives some evidence. He says, what you can do, these were experiments that were done by Mr. Boyle. So Mr. Boyle's experiments. And maybe I'll just read this short section of what he's talking about. He says, for one finds that the latter is really that which we feel and which we breathe, that is sound, and which being removed from any place still leaves there the other kind of matter, the ether, that serves to convey light. I'm reading about halfway down the first full paragraph on page 165. He says, this may be proved by shutting up a sounding body in a glass vessel from which the air is withdrawn by the machine which Mr. Boyle has given us, and with which he has performed so many beautiful experiments. So you might imagine taking a glass vessel, sometimes this is called a bell jar in physics and chemistry labs, so a jar like this, and you place it on top of a platform, maybe another piece of glass, and you have some kind of mechanism for suspending. Maybe you use very thin threads. I draw it like this, and suppose you were to suspend a bell inside of this. That would be your sounding body. You put a bell inside of here, and maybe you hang, I don't know, you have to come up with some kind of mechanism to ring the bell. Maybe you hang from the top some kind of hammer, but it's a magnet, perhaps, a magnetized hammer, and then you could hold a magnet. I don't know exactly how I did this. I'm just imagining how one might do this. You perhaps put a magnet out here, and then you use that to attract this bell back, or this hammer back, and then you remove the magnet, it swings forward and strikes this bell. And when you do that, you can hear the bell ringing, right? It rings, and you can also see the bell inside of this glass jar. And then he says, well, Mr. Boyle, he had been doing some experiments with vacuum pumps, and what he was able to do is attach a vacuum pump. I'm not going to draw a vacuum pump. Let's just suppose you have a vacuum pump right here. I'll just draw it schematically. You might imagine having a vacuum pump and a tube that you can hook up to this jar and pump the air out. And as you pump the air out, once you pump the air out as much as the vacuum pump will work, of course you can't get all of the air out, but you can largely remove the air. And when you do that, if you repeat this experiment, then the bell, when you ring it, doesn't make any noise. So if air is removed, the rung bell or the struck bell makes no sound. But, and here's the important point, but you can still see the bell. That means that whatever medium had been transmitting the sound, which has been removed, is not the same medium which is transmitting the light. Because if they were the same medium, then by removing it, not only would the sound go away, but the ability to see the bell would also go away. Therefore, there must be some other medium. That's the point that he's making here. He says, but in doing this of which I speak, care must be taken to place the sounding body on cotton or on feathers. I guess in my experiment, I talked about suspending it from dental floss or some string, so as not to transmit the sound through the solid object on which it's sitting. For then, after having exhausted all the air, one hears no sound from the metal, though it is struck. One sees here not only that our air, which does not penetrate through glass, is the matter by which sound spreads, but also that it is not the same air, but another kind of matter in which light spreads, since if the air is removed from the vessel, the light does not cease to traverse as it was before. Okay, that is the idea here. And then he also mentions some other experiments by Mr. Torricelli. And I'll just mention that, I'll write that down, even though I'm not going to spend, he doesn't spend as much time about Mr. Torricelli's experiments. Torricelli was another scientist who had done experiments with vacuum pumps. In fact, one of the measurements of pressure, we can measure it in pascals or atmospheres. You can also measure it in torr, or millimeters of mercury, and that's named after Torricelli. Anyhow, what Mr. Torricelli had done is he had taken some mercury. I don't know exactly how Torricelli had done this, but you might imagine, I'm imagining it in this way, you have a jar of liquid mercury, and you put a glass tube in it, and then you place some kind of piston right up against the mercury layer. So this is mercury inside of this cup. This is mercury. And this right here is a piston of some sort that can be drawn up this tube. And if you, in fact, do draw this up the tube, you can draw the mercury up this tube, but if the tube is sufficiently long, I guess I don't have enough space to make it really long here, but hopefully you'll get the point that I'm trying to make. If you make this tube really long, you can pull this piston up and draw the mercury up. Technically speaking, the air outside is pushing the mercury up, but you'll have to take Physics 201 to have a better understanding of that, perhaps. You can draw the mercury up, but at some point the mercury ceases to be drawn up, and you get a region above the mercury and below the piston that is a vacuum. Torricelli argues that this is a vacuum, and the point that's being made here is despite the fact that there is a vacuum in here, there's no air in there, you can still look through this glass tube and see the light coming through from one place to the other, so the light is transmitted through this glass tube, and hence, once again, it is not air or other kind of gas that transmit light. It must be some other kind of substance or other kind of material that transmits light. Okay, so so we've been talking about the matter in which this wave spreads, and he says it's a different kind of matter than the matter in which air spreads. And then finally, what he says is they have a different mode or manner of propagation. So the manner of propagation differs. So if the first way they differ is in their production, the second is the matter in which it spreads, the third is the manner of propagation. And here he reminds us of how sound travels. He says sound travels, and this is on the last, I guess the second to last full paragraph on page 165. He says that on the one hand, sound travels by air molecules or air particles colliding to produce compressions and rarefactions. So for sound, I can probably fit this in here, and I guess I talked about this in my last lecture, but maybe I'll reiterate this. If you have some kind of like a speaker cone that vibrates back and forth, and there are air molecules filling the space in front of it, when you move that speaker cone back and forth, you're going to get regions where you compress the air, that is, the air molecules bounce off of each other to produce regions of compression, and other regions where they're rarefied or made less dense. So you have these compressions and rarefactions of the air molecules as they're interacting with one another as a result of being pushed forward and backward. And you can make a plot of the density. So on the vertical axis here, I'm going to put the density. I apologize if this is being squeezed in here. And on this, the position. You can make a plot of the density versus position, and you can probably see that you have high density or high pressure air here, low density or lower pressure, high density, low density, and so on. And moreover, these regions of compression and rarefaction all move forward at some speed, and that speed in air is about 330 meters per second. That's the speed of sound in air at about room temperature and room pressure. So air is, he says, made up of these small bodies which are themselves able to move. This is the hypothesis of how air moves, of sound, how sound moves. It's comprised of these molecules that can bounce off of each other, and yet which are able to move away from objects moving through them. So we can take a baseball and throw it through the air. These air molecules can move around the baseball. They don't penetrate through the baseball. They move around it, and yet they can interact with one another. So that's kind of the theory of sound that he's proposing, or that he is advocating here. And he's going to argue that light is somewhat different than this. And in the next chapter, he's going to talk specifically about how the manner of propagation of light is similar in some ways, but different in other ways. And in particular, just as a heads up, he's going to say that these ethereal particles, the matter, the ether that is responsible for the conveyance of light, these have compressions and expansions like the air molecules in sound, but they differ in that these ethereal particles are able to penetrate solid bodies. They're able to travel through glass, through metal, and so on.